Hey everybody, it's time for another statics problem. This time we have from exam 3, fall 2017. This should be an internal force problem. Just 1 second while I get some on my computer. Let's take a look. Sorry, I probably should have paused the video, but at this point it's too late. So if you want to skip ahead the next 10 seconds or something, go ahead and do that. You'll see when I start doing some work. This is problem 2. Okay, sorry about that little pause there. We're going to go ahead and do some work on this problem. Yay, statics. So the problem says compute the internal axial force NB, the internal shear force VB, and internal bending moment MB at section B. I'll just draw a little line through that. For the frame shown below, note that the connection at C is a frictionless pin right here at C. That's cool. And all equilibrium equations must refer to a free body diagram or no credit will be awarded. Well, that's pretty standard. So we need to take a look at what we're doing here. We need the internal forces here at B. So hopefully you guys know that in order to solve for internal forces, we need to expose them somehow. And in order to do that, we need to make a cut through B. That's why I drew the line here, kind of a preemptive cut, if you will, at B. And then we need to use the forces that are acting all around it, or all the forces on one side of this cut to solve for the things at B. So what we need is we need to decide which side we're going to use. Well, looking at this free body diagram, I'm going to say that this side is going to be easier to solve for because this side has a hinge and a pin. It's just a whole bunch of kind of unknowns that I don't really care to do right now. So I'm going to use this left side here because all we have are the things at A. Now A is a fixed support, as you can tell by how it's drawn. So there will be an AY, an AX, and a moment about A. And we need to solve for all of those, which is where this problem gets kind of tricky. But ultimately, once we solve for those, it should be pretty simple finding all the internal forces here. So we're going to go ahead and take a look at this thing as a whole free body, or not, we're not going to take a look at it as a whole free body diagram right now, just yet. We're going to split this off into little parts to solve for it, because ultimately, if we were to try to solve for it as a whole free body diagram, I'm not going to draw it out, but like I drew here, we've got AY, AX, and MA. And here, we're going to have, this is a pin support, and it's on a wall, apparently. We're going to have DX. Well, that's 4 unknowns. We can't solve for 4 unknowns right now. Even if we were to take the moment about this point, we'd still have moment A, and it would be darn near impossible to solve for anything if we take the whole free body diagram. So we need to split it off. And so we're going to go ahead and draw this first section here, CD, off to the side here. I'm not going to use a straight edge because I like to live on the edge. We're going to go ahead and draw DX going that way like we have. DX. Next, we're going to have this pin, the reactions at the pin. And the reason they say it's frictionless is because if it had friction, I guess that would count as like a moment force or whatever. Instead, all we have is a CX, which I'm going to draw to the right, and a CY, which I'm going to draw going up. It doesn't exactly matter which way you draw them, just know how you're drawing them. Everything kind of has its purpose, I suppose. And just kind of remember that, because you're going to end up drawing the opposite with another free body diagram. We're going to go ahead and draw the dimensions into the 4 meters. And lastly, here it shows 400 Newton meters going to the left on this whole beam. And so that's kind of fun. I'm going to darken this line a little bit. Sorry, it's a little a little dry here, sitting here alone doing these. We've got 400 newtons per meters going to the left here. And that's everything that we need. We've got our reaction forces and our applied forces, as well as our dimensions. So now we need to solve for what are the forces? Well, the first thing we can do is take the moment about C, because if we were to take the sum of the forces, I guess we could take the sum of the forces in the Y, and we can do that. So sum of the forces in the Y, we end up getting Cy, but there's no other vertical forces acting on this besides Cy. So Cy is going to equal to 0. We'll draw a squiggly line under that. Next, you could solve for the forces in the X, but since we have two forces, two unknowns going in the X direction, that's not a good method because we're going to end up not knowing one of them, and we'd have to do another step anyway. So to save us a little bit of time, we're going to go ahead and take the moment. We could take the moment about either point now, since we found what Cy is. But I'm going to go ahead and take the moment about C. I guess if you took the moment about D and we still didn't know what Cy is, Cy would not cause a moment because it's acting in line. So in this particular problem, there's really no wrong place to take the moment, but just make sure that with every choice that you make, there's reasons behind it. So we'll take the sum of the moments about C. And here we've got dx, and it's 4 meters down. And it would be going counterclockwise, so it's going to be a positive moment. And then we're going to have our 400, which they're going to be going clockwise. So negative 400. The whole distance is 4. We need the middle part. That's where the, I guess, resultant force would be acting. And so that's where the moment would be causing about would be half of this 4, so it'd be 2. And then that's going to be equal to 0. Just to explain that again, we have the 400 newtons per meter. These 4 meters gets it into the total force caused by this distributed load. And then this 2 meters here is the distance from C to wherever that force is acting, or at least where we kind of predict it to be acting, I guess, or assume. So we're going to go ahead and solve for dx. Dx is going to end up being, we're going to add these to the other side, so positive 400 times 4 times 2, and then divide it by 4. We get 800. Excuse me, 800 newtons. It's going to be going to the right because it's positive, and that's how we drew it. Next, we could solve for the moments. I'm going to go ahead and do some of the moments about D. We could do some of the forces in the X, but when you do that, you leave the risk of, if for whatever reason you didn't get dx correct, then you're not going to get cx correct. So if you do the moments about D, that means that cx kind of stands by itself. And you can solve for that correctly while not solving for dx correctly. It's kind of just a way of covering yourself. And you can even do that to check your work, so once you find cx and dx, you can sum the forces in the x and it should equal 0. But enough talking, I'm going to go ahead and do this. We're going to have a negative cx times 4, clockwise. And then kind of the same thing here, but this time distance is still 2, it's going over 4, but it's going to be positive because it's going counterclockwise, so plus 400 times 4 times 2 is equal to 0. So Cx is again going to be equal to 800 newtons going to the right. Just to check our work here, we've got 800 plus 800. They're both going to the right. We've got the 400 newtons per meter going to the left. Well, if we were to calculate the whole force caused by this 400 newtons per meter, you would multiply the 400 times 4, which gives us 1600 newtons going to the left. So 1600 newtons going to the left and 800 plus 800 is 1600 newtons going to the right, would cancel each other out. Therefore, we got the right answer. And that's why I like to solve for the moments to find both, just so you can always check your answer and cover yourself. We can draw little squiggly lines here. The next thing we're going to need is the free body diagram of ABC. So I'm going to go ahead. I'm going to turn my paper to the side because I draw a little better vertically like this. And just draw a thick line here. Somewhat. It's not perfect. You might want to do with a straight edge when you're doing it, and just make it thick and darker than the rest so they can kind of tell what is the beam. Or you could draw it out and like make a little box, but either way, whatever works best for you and how you like to draw and see your free body diagrams. But anyway, we can start with the reactions at A. So as I drew earlier, we've got AY, AX, and the moments about A. So that's kind of cool. And then at the end here, we've got CY and CX because that's at the pin. But since we drew them going this direction here, we're going to have to draw them going the opposite. So CX is going to the right in this free body diagram. We're going to draw it going to the left. And then CY is going up in this free body diagram. We're going to draw it going down. And that's just equal and opposite forces. Because they're not moving, that means that this force, the forces at this point would be put on this are going to be equal but opposite to the forces done by vice versa. Kind of a bad way of putting it, I suppose. But hopefully you guys know it by now. Next, we're going to have our distributed load going across the whole beam. And it's going to be 200 newtons per meter. And then they give this in 3 meters and 3 meters across B, but right now we're just solving for the reaction forces in the whole thing. So I'm just going to say 6 meters across the whole thing. Make it a little easier. Well, we have CY and CX, and we got CY is equal to 0. And so with CX, I kind of broke one of my rules here. One of my personal rules. It doesn't really matter whatever you guys do. It's not a rule of statics or anything. But when I solved for CX here, I drew it going to the right. Ultimately, for internal forces like hinges and stuff like that, I just like to leave them positive, just to say, yes, I drew it correctly here. Because if I say it's going to the right here, it would actually be going to the left down here. So if I were to report it as going to the right up here, it might get kind of confusing when we get down here. So I'm just going to leave it as positive, meaning that whatever direction we draw it in, that's the correct direction. And that's going to be equal to 800 newtons. Well, now we can go ahead and solve for our reaction forces here. So we'll go ahead and I'm going to sum the forces in the X first. So sum of the forces in the X, we've got AX, and the only other force in the X is 800, and it's going to the left, so we'll say negative 800 is equal to 0. So therefore AX is equal to 800 newtons. And this time we can draw it going to the right because it actually is a support reaction. Next we can sum for the forces in the Y because we only have one unknown there. That's going to be equal to AY, and then we've got the 200 newton meters going the entire, 200 newtons per meter going the entire 6 meters. And it's going down, so minus 200 times 6. And then CY is equal to 0, so these are really the only two forces in that direction. We set that equal to 0. Therefore, AY is going to be equal to 1200 newtons. And it's positive, so it would be going upward with how we predicted it. And next, we're going to have to solve for the moment about A. So the moment about this point A here. We're going to first have MA, the moment at A. And the only other force that'd be causing a moment is actually going to be this distributed load, because AX and AY are at that point, so they don't cause a moment. They're at that point. It's kind of like I like to say, if it's like a nut and bolt and you have a wrench, it's like if you're just trying to push on the wrench versus trying to twist it. You don't do anything to loosen it. Out here, CY, oop, my bad, my other video that I made earlier just started playing and startled me a little bit. Happy Halloween. I lost my train of thought. So CY is equal to 0, and so it wouldn't be causing a moment about the point here. So all we have is this distributed load, and it would be going clockwise, so minus 200, and the whole load, the whole force of it is going to be times 6, and then it would be acting at halfway there, so 3, and that's equal to 0, and therefore MA is going to be equal to 200, had a little comma in there, 200 times 6 times 3, and so it's going to be 3,600 newtons, and the way we drew it was correct, so we're going to go ahead and draw it like that. And those are our reaction forces that we need. Well, we're not done. Isn't that great? You do all this work and you're not done with it. What we need now is what the question was asking, the internal forces at B. Well, in order to solve for that, we need another free body diagram, this time using the cut at B. So we're going to go ahead and draw this out. This time I will draw it as a thick beam here, I just like it for internal forces. It helps me see it a little better. It's, I guess, a little more eye-catching, I suppose. We can go ahead and draw everything that we know on this. Well, the first thing that I think is easiest is we can start with the reaction forces. So we've got AX going to the right. We'll just write it as 800 newtons. We've got AY going up 1200 newtons. And then the moment about A going counterclockwise, 3600 Newton meters. Oh, I drew that wrong. Newton meters for the units there. So you've got that. Next, we can draw the distributed load, and this is going to go all the way to the end here. This time it's not the end of the whole beam, it's the end up until B, but it's still going to be 200 newtons per meter. That doesn't change. What changes is the distance below, which from A to B is 3 meters, and that's what this whole thing is A to B. So that's going to be 3 meters. Next thing is we need the internal forces at B, and this is where I can't stress enough. One of the most important things that you're going to need for internal forces is knowing the conventions of how things are drawn. So I'm going to draw them in as they are here. First, we've got the shear, and we've got it going down, V. We're going to have VB is what they wanted us to label it, because it's at point B. So we'll label it VB. Next, we've got the axial, which is going to always be going out, NB. And then we've got the moment, which is going to be going up, MB. Or not up, but in this case, counterclockwise. But it always kind of curls around that end. And that's what we've got for the internal forces here. Always remember the conventions here. On like this cut here, on the left side of the cut, this is how we draw it. V is always going to be going down, and is always going out, and then MB is always going to curve up and around. If we were on the right end, I'm going to draw a little sketch down below. It's not going to matter. Do not put this in your exam and your work. But just know V would be going upward on the right end of the cut. N is always going to be going outward. N is kind of like, if you think back to our trusses are always drawn with the arrows pointing out from the point. That's because we assume them to be a tension, because tension is positive. And we're going to assume that the normal force is in tension because tension is positive. And last, we're going to have our moment, which our moment is always going to curl up and around. I always like to think of it as if we were to make a cut here or on a beam, the cut on this end is going to have to be counteracted by the moment on this end. Ultimately, this would form into a smile. So if I took my ruler here, I finally have one, is you would want to apply moments on the end to make it curl into a smile. And so the moments on the end would be going like this. And when you know that, you can kind of assume what the moments would look like on the other sides of the cut. Hopefully that makes sense. Otherwise, it's kind of up to you to finding your own ways of memorizing the actual conventions. It's just something that you have to know. I feel like there's not a lot of memorization in statics as it is just knowing processes, but something that you do have to memorize. So we got the internal forces here. Now it's just equilibrium equations, which isn't too bad. So if we wanted to solve for, let's say we solve for the normal force first, we'll go ahead and solve for the forces in the x. The only unknown should be the normal force. So we'll go ahead and start with NB. And if we look, the only other force going in the x is going to be our 800. So plus 800 is going to be equal to 0. There's no other forces there. So therefore, NB is going to be equal to negative 800 newtons. And this is where these internal force problems kind of contradict how I normally do statics problems, maybe how you would too. With these, never, ever, ever draw arrows with them. We have these sign conventions for a reason, and that's because we want people to always know what we mean by the positive and negative signs, because we want to leave them in positive and negative signs. It's kind of like what I was talking about before with the CX and the CY, how I drew an arrow here at CX and I didn't want to. Well, that's because here at CX, if it's going right here, it's going to be going left here. I didn't want to say what direction it's going because that could get confusing. If I draw an arrow to the right, they think, is it going right here? Is it going right here? I don't really know. You want to leave it as positive and let your free body diagram do all the directional talking for you. Kind of the same thing with internal forces, is you want to leave this as a positive or a negative, and then let convention and your free body diagram let people know what direction it's going in. So that's why it's always so important, is because you need to know if it's positive or negative. You can't draw the arrow and say that's good enough, because that's not how these are supposed to work. It's a little different, but it's not as direct, but hopefully people already know the conventions, and then science should just fall through and make sense. And so we can go ahead and draw that down here. Negative 800 newtons. If I take a look here, yep, should be negative 800 newtons. Next, we're going to solve the forces in the y, and that should get us our VB. Our VB is going down, so I'm going to go ahead and draw negative VB. And now we need to find all the forces in the y. Well, we've got 1200 going up, so plus 1200, and it's going up. Then we've got the 200 newtons per meter. It's going down, so minus 200, and the entire distance is 3 meters, so we'll multiply that out. And there aren't any other forces going up or down in the y direction, so we can set that equal to 0. Therefore, VB is going to be equal to, and we're going to add VB to the other side, if that makes sense. So we're going to have, get that glare out of the way, 1200 minus 200 times 3. We're going to have VB is equal to 600 newtons. And again, we got a positive number. We're just going to leave it in positive, because conventionally, if we, when it's going down, that kind of means negative going down. But ultimately, it's going to be positive just because it's following through with exactly how we expected it, how we drew it. So it's a positive 600 newtons. And lastly, we're going to do the sum of the moments. Sum of the moments, and this time we're going to do the sum of the moments about point B here, or the cut, or whatever you want to call it. I'm going to say sum of the moments about cut, because it could work for any point. But sum of the moments about cut, or sum of the moments about point B, we're going to have MB, and it's going to be going positive. This right-hand rule, counterclockwise, positive. The other moment, we're going to have to keep track of all the forces that cause moments. Well, we have this applied moment here, this 3,600 Newton meters here. Well, no matter where that's acting, that is just going to be a flat 3,600 Newton meters. Applied moments don't matter. It doesn't matter where the distance is from the point on those. They're just applied. They are just the moments by themselves. So we're going to have, and it's going to be going positively, so plus 3,600 at no distance. So it's just there. It could be here on the end here, it could be in the middle, it could be right here on this end. It's going to be 3,600 wherever it is. Next, I'm going to go ahead and take into account this 1,200 newtons. This one is going to be going clockwise, so minus 1,200, and this is just a force, so distance does matter, times 3, and that's it. And then next thing we've got is the 200, and this is going to be going counterclockwise, so plus 200. The total distance is 3, and so the partial or halfway distance where it would be acting is 1.5, and that's going to all be equal to 0 there. Okay, and if you need to think about it in terms of unit analysis. This is going to be in Newton meters because it's already given Newton meters. This is going to be newtons times meters, so it's going to be in Newton meters. That's our moment units. And this is going to be newtons per meters times meters times meters, which ends up making it Newton meters. Maybe how I said it is just confusing, but if you're in doubt, always just take a look at the units and how you're doing it and think about how they work with the math equations, and it should kind of fall into place. So we're going to go ahead and solve for this. MB is going to be equal to, get the paper out of the way, get my calculator in here. All of this is going to be on the opposite side because MB is going to be positive on this side. So all of these are going to be, when I punch it in my calculator, negative of what their values are. So we're going to have a negative 3,600 plus 1,200 times 3 minus 200 times 3 times 1.5. 3600, 1200 times 3, negative 200 times 3 times 1.5. Okay, I always like to check. And we get a negative 900 Newton meters. And again, leave it negative. That's the biggest thing. I've seen quite a few exams and homeworks in the past where people don't. And it's unfortunate, but it's going to be a few points that you're going to lose there. But anyway, that is how you would go about solving for internal forces in a problem like this. A lot of the work was actually just spent solving for what the reaction forces are. And that's, I think, a big important part with internal forces is you just need to know how to frame the problem. You need to know exactly what you're looking for. You need to know where the cut is going to need to be, and then you're going to need to think about which free body diagram with the cut would be easiest to make. So I chose the left side because there's a lot less going on there than on the right side. But if for whatever reason you wanted to choose the right side, you very well could. It might be a little more complex, but it might make more sense to you. It might save you more time. It would have saved us maybe a free body diagram had we just kept it here. But still, it's always up to you and what you need to do. So that's everything I have for this. Hopefully it made sense to you guys. Let me know if it doesn't. You can always comment or email me or whatever. But thank you for watching and good luck studying.